ഹലോ ഡെൽവിൻ, വോയിസ് ഓക്കെ അല്ലേ?
സർ ഓക്കെ ആണ്.
സ്ക്രീൻ പ്രസന്റേഷനോ?
പ്രസന്റേഷൻ ആണ് സാർ.
ശരി. ഇന്നലെ എക്സാമിന് എങ്ങനെ സമയം കഴിഞ്ഞോ ഇഷാദ?
സർ
എക്സാമിന് സമയം ഓക്കെ ആയിരുന്നു ഇന്നലത്തെ?
സർ ഓക്കെ ആയിരുന്നു.
ശരി. അത് അറിഞ്ഞിട്ടാണ് ഒരു അരമണിക്കൂർ അധികം തന്നത്. കഴിഞ്ഞ പ്രാവശ്യം നിങ്ങൾ എക്സാമിന് സമയം കിട്ടില്ല എന്ന് കുറച്ച് പേര് പറഞ്ഞിരുന്നു. Okay, I hope I'm audible and you are able to see the presentation also. So let's get started. I will start off from with a quick review of the previous classes material. All right. So in the previous class, we had seen the realization of FIR filters, and we had said that we have mainly four different kind of realization. The first one was this transversal structure, and it is also called as the it is also known as the direct form realization. And the method is quite straightforward. We just find the transfer function h of z of this equation, then we are directly realizing it just by looking at the equation. So this was how the transversal structure was developed. So you have x of n, then you will be taking h of 0 without any delay, then h of 1 with 1 delay, h of 2 with 2 delays. Then finally you will add all the terms to get the transversal realization. And we had seen one example also. And I had also mentioned we can have two different kind of orientation for the same structure. And the second one seems to be quite useful when you are going for a cascade realization. So we had also looked at an example for a cascade realization where a polynomial will be given in the form of a product of two different polynomials, and we can realize each of those individual polynomials in direct form or the transversal structure. Then we cascade it, so you will get that cascade realization. And we had also looked at some example of doing it, and I had also said that if the polynomial is not given in the form of a factor, we have to factorize it. I think is there an option for solving third degree polynomial in a calculator? Can someone reply me?
sir.
ഉണ്ട്. Okay. More than 3 ഉണ്ടോ? 4, 5 ഒക്കെ ഉണ്ടോ?
ഇല്ല സർ.
All right. I don't know whether some online tools are available to solve the fifth degree polynomial also. I think MATLAB has a provision for solving any polynomial of any degree. Okay. There is a function called solve, and if you have MATLAB, you can explore it. Okay. So we stopped at that point. That is, we realized a cascade structure, and we found the different factors by long division. Then we wrote it back in the order in which we have it is convenient for realizing the structure. Then we had realized the structure as well. Okay. Now we are going to yet another realization form of an FAR filter. It is called a linear phase filter. This is really simple, and it is quite interesting also. So let me start with some theory or the math required for the development. So we have a class of filters known as linear phase filters. Okay, linear phase filter means I will just give you just a introduction. That is, if the phase angle of that filter or the change in phase with respect to frequency would be a constant into the frequency. Okay, the phase angle changes directly proportional to the frequency. Okay, so that is the meaning of linear phase filter. Actually, this is an equation for a linear equation, or it is an equation for a straight line. Okay, so this is happening in the frequency domain. That is, if you are finding the frequency response or a Bode plot of that particular filter, and if you are plotting the phase response, you can see the phase response is behaving in a linear way. That is, it would be always a straight line. So that is how it looks like in frequency domain case. But if you are looking at the filter's impulse response, the h of n would be always satisfying this property. H of n would be equal to h of n minus 1, where the capital N is the number of samples. N is the number of samples. Okay. So what does this equation mean? So I have I have written an example for a linear phase filter which obeys this property. So let's look at how this property is being obeyed. So I have given the impulse response of such a filter as h of n equal to 1, 2, 3, 2, 1. Okay, it is 1, 2, 3, 2, 1. So if you look at this equation, I'm going to write the sample of h of 0. So these are the indices 0, 1, 2, 3, 4. Okay, these are the indices of the impulse response h of n. The values are 1, 2, 3, 2, 1. Okay, so if I write h of 0 is actually 1. Now if you are finding h of n minus 1, so here in this case the value of capital N is 5. Okay, because we have we have 5 samples in the impulse response or the signal h of n. And if I find h of n minus 1, you can write capital N is, so this is capital N. Capital N is 5. Small n is the index that we are taking at this instant. So n is 0 over here. So this is 0. And we have the 1 that is written as 1. So that is equal to h of 4. So this property says that h of 0 is equal to h of 4. So that is actually obeyed in this case because h of 0 and h of 4 are equal in our case. Okay. So so I have already said that this is an example for a linear phase filter. So if you look at the linear phase filter, this property is being obeyed. What does this property say? H of n equal to h of n minus 1. Okay. Now let me take the next sample. H of 1 is equal to 2 because the second sample is 2. Suppose that I'm going to find h of n minus 1. Capital N is 5. Small n at this instant is 1 minus 1, which is equal to 5 minus 1 is h of 3. So you can see that h of 1 and h of 3 are equal. So let me give a different color. Okay. So you can see that you already seen that h of 1 and h of 4 are equal. And similarly, h of 2 and h of 1 and h of 3 are equal. Now let me take the next one, that is h of 2 equal to 3. H of 2 is equal to 3. So if I find h of n minus 1, here it is 5. 5 minus 2 is 3 minus 1 is 2. So h of 2 and h of 2 are equal. So this we are getting the same sample. So h of 2 and h of 2 are equal. So this is a single sample. So what does this mean? This means that the impulse response is symmetric. Okay, the sequence values are symmetric. And if you again move to find the next sample, we had already exhausted the samples, checking the sample. So even if you find, even if you go for h of 3, we have the values 2. H of 3 is 2, and h of that value is equal to h of n minus 1. So h of 5 minus 3 minus 1, 5 minus 3 minus 1 is h of 1, which means that h of 3 equal to h of 1. We had already found that equation over here, h of 1 equal to h of 3. Okay, and even if you move further, if you find h of 4 is in fact 1. That is equal to h of 5 minus 4 minus 1, that is h of 0. So h of 4 and h of 0 are equal. We had already examined that equation in the first case itself. Okay, so what does it say? This says that the impulse response is symmetric with respect to its center point. Okay, so that is the property of a linear phase filter. Okay, so if that property is being obeyed, then we can have some improvements in the structure realization. Okay, so this is the case when I took the value of n equal to 5, where 5 is an odd number. Okay, so let me write that point odd number there because it has got some significance. Now let's take another example. I'm taking another example, h of n. So this is 5, 2, 4, 1, 1, 4, 2. So here you know that the capital N is the number of samples. Number of samples n is in this case it is 6. It is an even number. Okay. So let's take whether that property is let's check whether that property is being obeyed. So here I have h of 0. H of 0 is 2. And let me find h of n minus 1. That is, I'm finding h of capital N minus small n minus 1. Okay, if I find that, it is h of 6 minus 0 minus 1. This n is the index that we are considering right now. It is 0 over here, so it is h of 5. So this says that h of 0 and h of 5 must be equal. And if you look at the values, h of 0 and h of 5 are equal. And if you consider the indices as 0, 1, 2, 3, 4, and 5. Okay. And let me take another example, that is h of 1. H of 1 is actually 4, and it is equal to h of 6 minus 1 minus 1, which is 4, h of 4. We can see that h of 1 and h of 4 are equal over here. Okay, idum equal. And if you take the next point, h of 2 equal to 1. Okay, and if you examine h of n minus 1, it is h of 3, and you can clearly see that h of 1 and h of 2 and h of 3 is having the same value, so both of them are equal. So these are the filters that is obeying this property. Such filters are known as the linear phase filter. Okay, and if I write another example, let's say h of n equal to 1, 2, 3, 1, 2. Is this an example for a linear phase filter? Can you just tell me? Is it an example for a linear phase filter?
No,
Anyone?
sir.
Okay, it is not an example for a linear phase filter because it is not symmetric. Okay, so if it was a linear phase filter, then this and this must be equal. That is not equal in this case. This point and this point must be equal. That is also not equal. And this 3 is a single point or a lonely point. So we don't want to consider it. Okay, so that says that a linear phase should be symmetric with respect to its center point. Okay, that is the takeaway from this particular discussion. Okay, and keeping that in mind, let's move to the realization by taking an example. Okay, so let me consider h of n equal to 2, 4, 1, 1, 4, 2, the same one that we had considered in the very previous example, where we have the value of n is equal to 6, and which is an even number. Okay, and if I find the z transform, okay, so if you have h of n, if you want to find h of z or the transfer function, then it is just finding the z transform of the finite length sequence, that is sigma n equal to 0 to n minus 1. Actually, the equation for z transform of any sequence is in fact n from minus infinity to infinity, h of n z raised to minus n. Okay, as this sequence is being a finite length sequence, the sequence exists only for 0 to capital minus 1. So you don't want to take the summation from minus infinity to infinity. You can take it from 0 to n minus 1. Okay, so that is why the equation is wrote in this form. Okay, and let me find the transfer function of this particular sequence. So you have sigma n equal to 0 to n minus 1 h of n z raised to minus n. So here it is 0 and n minus 1 in this case would be n equal to 6. So n minus 1 would be 5. Okay, so we are in fact finding the summation from 0 to 5. So what will happen? The first one value is h of 0. H of 0 is 2 and the power is z raised to minus 0. So I'm writing the z raised to minus 0 even if the value is 1 because that will make the generalization of this equation similar in the later stage. Okay, so you have 2 z raised to minus 0. Next one would be 4 z raised to minus 1 because here it is minus n, so the powers will be always negative. And you have the next one that is 1 z raised to minus 2 and you have the 1 over here again 1 z raised to minus 3, 4 z raised to minus 4 and 2 z raised to minus 2. So this is in fact an example for a linear phase filter because you can see the symmetry with respect to its middle point or the center point. That is, it is actually 2 is at the end, 2 is also over here, 4 is here, 4 is here, 1 is there, 1 is there. Okay, so this is in fact an example for a linear phase filter. Now what we can do is as the coefficients are equal in the either halves, so you can group the same coefficient terms together. Okay, so that means that you have 2 z raised to minus 0 and 2 z raised to minus 5. So you can group them together because both of them have the same coefficient of multiplication. So you can take it outside and you can write it 2 z raised to minus 0 plus 5, 2 into z raised to minus 0 plus 5 z raised to minus 5. Similarly, you can group this term and this term together. So it is 4 z raised to minus 1 and 4 z raised to minus 4. Okay, so you can write it as 4 into z raised to minus 1 plus z raised to minus 1. And here you have two different terms, that is z raised to minus 2 and z raised to minus 3. And both of them has the same coefficient. So what you can do is you can take that coefficient outside. So here the coefficient is 1. I have intentionally wrote that. So here the coefficient is 1 and you have inside the bracket you can write 2 raised to, sorry, z raised to minus 2 and z raised to minus 3. All right. Now, can someone tell me, sorry, can someone tell me, 1 second. Okay. Okay. So can someone tell me what is the advantage of, if you are going for a realization, what would be the difference between these two forms, or what advantage will we have if you write the equation in the second way rather than the first method, or what would be, or which would be better if you are, or what equation would be better if you are going for a realization, just by taking this equation as it is or by taking this form, or what advantage has got either of them? ആർക്കും പറയാൻ പറ്റും?
നമുക്ക് മറ്റേ പാരലായിട്ട് എടുത്താൽ മതി.
പാരലായിട്ട് എടുക്കാം because two terms has the same coefficient. അതാണോ ഡെലിന് ഉദ്ദേശിച്ചത്?
ആ സർ, അതാണ് ഉദ്ദേശം.
Okay. What about the number of multiplications? If you consider the two equations, is there any change in the number of multiplications that we need to perform? Multiplication means you have the coefficient as well as the signal, or z raised to minus 0. If you are writing z raised to minus 1, we are actually multiplying with x of n minus 1. Okay, that is actually happening. So what about the number of multiplications used in the first equation and the second equation? Can anyone comment on that? Anyone?
Second one look കുറവ്.
Yes, second one നമുക്ക് number of multiplication കുറവാണ്. Okay, is there any improvement in the number of delay units that we need to use? Can anyone comment on that? Anaka, what's your opinion? Is there any change in the number of delay elements that we need to use?
Sir, I think it will be reducing.
Okay, you think it is reducing. Okay. Anyway, the number of multiplications are reduced because you have a summation over here and it is multiplied with 2. You have another summation over here, it is multiplied with 4. You have another summation over here, it is multiplied with 1. But if you look at the first form, it is you have a multiplication over here, another one over here, another one over here. Because even though it is 1, if it was some other points, it would be a multiplication. You have another multiplication over here, another one over here, another one over here. So you have 1, 2, 3, 4, 5, 6 multiplication, but in the second case you have only 3 multiplications. So the number of multiplications has reduced. That means that if you are going to implement it in a computer, the number of multiplications are reduced. That will be saving some time for completing the process or completing the calculation. And as far as the delay element is concerned, I think, or we do not have any savings on the number of delay elements because you have z raised to minus 1 is there, z raised to minus 2 is there, and all the way up to z raised to minus 5 is also there. So we will need 5 delay elements for the first kind of realization, and we also need the same number of delay elements for the second kind of realization. Okay, so let me just stop at this point. Okay, and let me come to the realization, and I will explain these two equations after once the realization has been finished. Okay, so this second equation, that is enough for us to perform the realization of this structure. Okay, so if you want to realize this structure, you can see that we can have two delay elements grouped, and it is multiplied with a single value of coefficient. Okay, so let me copy this equation. So otherwise, okay, so let me, this is my h of z. Let me copy this equation. Okay. So this is what we want to realize. Okay. So for this realization, let me clear off these lines. Okay. So for this realization, suppose that I have the value of x of n over here. I have the value of x of n over here. Okay. And we have a z raised to minus 0 term, that is, we do not have to pass the signal through any delay element. And we have to pass another signal, or we have to pass the next one with we have to pass the next one with z raised to minus 5 or 5 delay elements. Okay. Similarly, we have another one, that is, we have to pass the 4 with 1 delay element, and the second z raised to minus 4 it will be obtained after passing it through 4 delay elements. Okay. So what I'm doing is I'm going to draw the delay elements first. So I'm evenly distributing that delay elements z raised to minus 0. So that is one delay element, and we should have to have another delay element, that is z raised to minus 1. So you have two delay elements, and let me draw the third delay element over here, that is my z raised to minus 3. Okay, that is my z raised to minus 3, and another delay element over here, that is again z raised to minus 1. So you will get z raised to minus 3 term over here, and you will get z raised to minus 2 term after this delay element, and at the end you will have another term that will be with z raised to minus 1. So at this point you will get z raised to minus 5 value at this point. Okay, now let me group this, or let me realize this structure by using the first term first. So you have x of 0, sorry, you have z raised to minus 0 and z raised to minus 5. So you know that z raised to minus 5 is available at this point, or x of n into, or x of n minus 5 is available at this point, or x of z into z raised to minus 5 is available at this point. Okay, so I'm taking that value at this point. Then you have a z raised to minus 0 term, which is having no delay provided. So you can directly take that value over here, and you can sum it over here. Okay, so what you will obtain at this point will be z raised to minus 0 plus z raised to minus 5. Then you have to multiply that summation with 2. Okay, so what I'm doing is I'm taking a point from this location, then that is being given to, that is taken to this point. Okay, so this has to be multiplied with 2. All right, so this term is over. Next we have z raised to minus 1 and z raised to minus 4. Z raised to minus 1 is available at this point, or x of z into z raised to minus 1, or x of n minus 1. Then I'm taking that point, then I need to get z raised to minus 4. Z raised to minus 4 would be available after 4 delay elements. So here I have z raised to minus 4 available, and those two terms has to be added together. So I have z raised to minus 4 and z raised to minus 1 added. Then that particular delay has to be, or that particular sum has to be multiplied with a coefficient 4. Okay, so you got this term also. And at the end, you have z raised to minus 2 and z raised to minus 3. So z raised to minus 2 is available at this point, and z raised to minus 3 is available at this point, because uh, this point it is coming after 2 delay elements, and at this point it is coming after 3 delay elements. Then you sum it at this point. So you have realized this term. Then you take the output of that summation. Then you have to multiply that with 1. So you don't have to put 1 explicitly, that is known. Then you can add these terms. Okay, so I'm taking at this point, another at this point, and I'm adding to this one, and this one, and here you will be obtaining the value of y of n. So you can have the value of y of n in either direction. So let me draw it over here. So there is a summer over here, another summer over here, and let me take this to this one, this to this one, and here you will get the value of y of n. Okay, so it seems to be a bit involved, but it is rather simple for realization. Okay, so let me put the arrows correctly. So this is the direction. Okay, so you look at this equation. It has got a nice form, that is, you have a single term has to be multiplied, and you can group 2 delay elements together. So z raised to minus 0 plus z raised to minus 5 would be 1, would be taken from this point, another one would be taken from this point, and both of them can be added together. Then you multiply that with 2. Then you have the next one, that is 4 into z raised to minus 1 plus z raised to minus 4. So that can be added, and you can take it at this point, and the last one is obtained at this point, and you can add all of them together. You will get the value of y of n. Okay, so this is the realization that we have to find. Okay, is it clear? And you can draw this to your notebook. Okay, and let me know if you have finished it. So you can start, or you just draw this realization structure into your notebook. You just need this realization equation, then you just draw this structure also. Now let me know if you have finished, Delvin. Finished, Delvin?
sir. Sir, എനിക്കൊരു ഡൗട്ട് sir. ആ 1 കോഎഫിഷ്യന്റ് എടുത്താൽ നമ്മൾ z raised to -2 ഉം z raised to -3 അല്ലേ?
അതെ.
അപ്പൊ നമ്മൾ ഫസ്റ്റ് z ഇൻവേഴ്സ് നിന്ന് എടുത്തേക്കണതോ സം ചെയ്തേക്കുന്നത്? ശരി ഓക്കെ അല്ല സർ ആരോ ഉണ്ട് കുഴപ്പമില്ല. Okay sir.
Okay, so that is finished. So let me come back to the discussion where I stopped previously. So we have the form. So what I want to emphasize at this point is we just want to have this equation. Let me take it off. Okay, we just need this equation alone to realize the structure. By finding this equation in this form, we can directly realize it. Okay, and I have written some more equations over here, and I'm just discussing at this point, and it will be needed in fourth module. Okay, so let me write okay, one second. Okay, so you can write this 2 into z raised to -0 plus z raised to -5 in this way, that is 2 into z raised to -0, and here for finding 5 I'm applying the property of the linear phase filter. This 5 comes from the fact that it can be written as capital N minus small n minus 1, that is n minus n minus 1. 6 minus 0 minus 1 is 5. All right, then you have 4 z raised to -1, and this z raised to -4 can be written as 6 minus n minus 1, or n capital N minus small n minus 1. So here the small n is -1, so I can write it as 6 minus 1 minus 1, that is minus 4. And the last one is 1 into z raised to -3 and z raised to -2. So z raised to -2 is written as it is, and z raised to -3 can be written as z raised to 6 minus 2 minus 1. Okay, so what I can do is I just don't want to run the value of n from 0 to n minus 1. I just have to run the value of n for only few points, and you can have the value of 0. You can find the other index by using this form. You can have the value of n equal to 1, and you can find the other index, that is -4, using this form, where you just use 1 over here just like you use 0 over here. Similarly, you can also have the value of n equal to 2, and that 2 can be substituted over here to find the value of 3. So what this means is you can actually run or you can have the summation by taking the value of n from 0 to a smaller number, instead of running the value of n from 0 to capital N minus 1. So what is the value of that smaller value of n? Smaller value of n, the reduced value of n. So in this case, you have the value of capital N equal to 6. Okay, you have the value of capital N equal to 6, and the maximum value of n that we needed in this case is 2. So how will you find 2 from 6? The method is you can subtract 2, then divide it by 2. That is capital N minus 2 divided by 2. So this would be 2. Okay, so what I can do is I can just group these equations in a general form. Instead of running the summation from 0 to n minus 1, I'm running the summation from 0 to capital N minus 2 by 2, that is 0 to 2 in this particular example. Then the coefficient I need to multiply is the value of h of n. Okay, so I'm writing h of n. Then you have to have z raised to -1, that is the first one. Okay, in all cases I have written the first one, z raised to -n, and the second term is z raised to minus capital N minus small n minus 1. So that is written as z raised to capital N minus small n minus 1. Okay, so this is where the way how we can simplify it. So the point that you need to keep in your mind is, if the value of n is an even number, okay, note this point, if the value of n is an even number, the number 2, if the filter is a linear phase filter, then you can write the equation for h of z in this form. Okay, and we will see this equation in the fourth module. All right, similarly, so we had also already seen one example for where capital N is an even number. Let me take another example. So let the value of n is, or let the value of capital h of n is 1 2 3 2 1. Okay, so is it an example for a linear phase filter? Anyone? Agash, Pradeep?
Hello, sir.
Yeah, Agash, is it an example for a linear phase filter?
The linear ആണ് തോന്നുന്നു.
The confusion. Okay, confusion. Okay. Can someone help me, Adityan? What is your opinion?
Yes, sir.
Is it a linear phase filter? H of n is 1, 2, 3, 2, 1.
Yes, I think so.
You think so? Okay. അവിടെ ഉറപ്പായിട്ടില്ല. Then anyone else? Ashida? Ashita?
No, sir.
Okay. Is it an example for a linear phase filter?
Yes.
Yes. Why?
Hello.
Yes. Why? Why did you say that?
Sir, symmetric.
Okay. So it is symmetric. That is, it is one is there. Okay. ഓർപ്പ് വരാതെ just നോക്കാം. One is there, one is also here, and two is here, two is here, and you have the three as the single point. So it is actually symmetric with respect to its midpoint. Okay. I think this was the simplest point, and this is the most talked about point in this class. Okay. And you just clear your confusion at this point. Okay. So if this filter is symmetric with respect to its middle point, then the filter is actually a linear phase filter. So if it is a linear phase filter, we can in fact write h of n as h of n equal to h of capital N minus small n minus 1. Okay. So this can be written in that way. So we will check that out now. So I can write h of z equal to sigma 0 through n minus 1 h of n z raised to minus n. So this is 1 into z raised to 0 first term, 2 into z raised to minus 1, 3 into z raised to minus 2, 2 into z raised to minus 3, and 1 into z raised to minus 1. These are the indices 1, 2, 3, and 4. All right. Now what I'm doing is we are grouping the same coefficients term together. So I'm grouping this one and this one and this one, and we have a single point which do not have a pair to group with. So you can keep it alone, and you just manipulate the other terms. Okay. So you can write this one, that is 1 into z raised to minus 0 plus z raised to minus 4. So we have taken care of the first and last terms, and 2 into z raised to minus 1 plus z raised to minus 3. So we have taken care of the second and the fourth term, and we have writing the third term alone. Okay. Now what I can do is I just need this equation for realization. Okay, and I will write a generalized form or below this one. So you can write it as 1 into z raised to minus 0 plus z raised to minus n minus n minus 1. So this minus 4 can be written as capital N minus small n minus 1. Similarly, this 2 into z raised to minus 1 and minus 3 can be written as z raised to minus 5 minus 1 minus 1. Okay. And similarly, the last term is written without any change. Okay. Now, if you are going to write the generalized form, here we had the value of capital N equal to 5. And if you look at this equation, you just need to run the value of n only from 0 to 1. Okay. So the way to get the number 1 from number 5 is you can actually write n minus 3 by 2, which means that here you have n is 5. So n minus 3 by 2 would be 2 by 2. That is 1. Okay. So you have to run the summation from 0 to n minus 3 by 2. So I have written as n equal to 0 to n minus 3 by 2. And the first term is h of n. And inside the bracket, you have z raised to minus n, z raised to capital N minus small n minus 1. And not only that, we have one more term left, that is the middle term. So the middle term's index is here 2. So you can find that 2 by using n minus 1 by 2. So here you have 5 minus 1 by 2. So that is 2. Okay. So the single term can be written in this way, that is the index can be found by using the value of capital N, that is h of capital N minus 1 divided by 2 into z raised to minus of n minus 1 by 2. So this is the general form, and we will need it in the fourth module. So you can go ahead with the realization just by using the equation that I have just wrote in the second line. So you can take this equation, and if we want to find the generalization, and I'm taking this equation. So this is my h of z for our example. Now how this can be realized? How many delay elements needs to be drawn? Anyone?
4.
How many delay elements?
4.
we need to draw 4 delay elements. So you draw it symmetrically, and that would be that is required, and that is how we get the realization in a neat form. So we need 4 delay elements. So let me draw it symmetrically like this. Okay. So you have z raised to -1, z raised to -1, z raised to -1, and z raised to -1. Okay. Then what should I do as the next step? Anyone? Or what are the terms need to be added? So let me draw the lines also. So from here to here to here to this point, and somewhere it will be here. Okay. So you have to take z raised to -0 and z raised to -4. Z raised to -0 available at this point, and here you have the x of n. Z raised to -4 is available at this point, and you need to add them together. So I am adding them. Okay. This is added, and that sum need to be multiplied with 1. So you are multiplying it with 1. Okay. And the next one you have 2 raised to 2 into z raised to -1 into z raised plus z raised to -3. Z raised to -1 can be taken from this point. Z raised to -3 can be taken from this point. You just add them together, take it outside, multiply it with the gain, that is 2, and you have a single term over here. Okay, where should I tap that single point from? Anyone? How would I draw the structure for 2 z raised to -2?
Center.
Okay, you can either take from this point, or usually it is drawn something like this. Okay, you take it from this point and you can put a gain over there. Okay, then what we are doing is we will be summing all the terms together. So this is plus, this is plus, then you take the entire summation, and whatever you get at the output, it is y of n. Okay, and one thing that you need to notice is the advantage of drawing the linear phase realization is you can reduce the number of multiplications. Okay, so if it was not the linear phase realization, if you just take the example of this case, if it was not the case of linear phase realization, you'll have to multiply z raised to -1 with 4, again z raised to -4 with 4. Okay, but what we are doing now is you have taken the summation first, then you are multiplying with a single gain. The number of multiplications has been reduced. Otherwise we would have to multiply each of the delays with each of the gains. Okay, so the advantage of linear phase realization is the number of multiplications has reduced. Okay, and that applies for any kind of linear phase realization. The number of multiplications can be reduced, just like we reduced the number of delay elements when we realized the direct form 2 of IIR filter. Okay, for IIR filter we studied both direct form 1 and direct form 2. In the case of direct form 2, we had reduced the number of delay elements. Just like that, we are reducing the number of multiplications in this realization, that is the linear phase realization. And if the question asks, or if you're asked to draw the realization using minimum number of multipliers, and you have to realize the structure in linear phase realization if it is a linear phase filter. Otherwise you have to go with the transverse realization or a direct form realization. If the filter is a linear phase filter, and you can see the property that h of n equal to h of n minus n minus 1, then in that case you can decide that it is better to realize it in linear phase realization, because there will be a savings in the number of multiplications or the multiplications operations. Okay, so you can draw this figure also. Delvin, please draw it to this your notebook and let me know if you have finished.
Yes, sir.
All right. So let me take you to an example, that is the linear phase, an example for finding the linear phase realization. So in the linear phase realization, I have written h of z is, the question is given as realize the system function in linear phase realization or using linear phase realization. So I have given you an equation that is h of z is given in this way. So do you think this is a linear phase filter? Agash, again, is this a linear phase filter? I think it would be clear by now. Oh no.
ഇത് linear phase filter ആണ്.
Why?
മറ്റേ symmetrical അല്ലേ?
Okay, coefficients are symmetrical because 1/2 is there in the beginning, at the end also. Okay.
1/2.
So this is 1/2 and that 1/2 is there. This is 1/3, 1/3 is there. And here you have 1 and that 1 is there. And the middle you have 1/4. Okay. So how many delay elements should be required, Anupama? How many delay elements should be required?
So 6.
6. So you will have to distribute 6 delay elements evenly on top and bottom. So I'm writing z raised to -1. Then let me copy this down. So another one, another one, another one. You have another one, and you have already 6 delay elements. Right. Now what should I do? I'm taking x of n at this point. I'm taking x of n at this point. So let me draw this way. Okay. Now I need to find the grouping. Okay. So before we move to the realization, let me write it in a grouped way, so that would be helpful for you to get the things done. Okay. So you have 1/2. So you have z raised to -0 in the beginning. At the end, you have z raised to -6. So you have taken care of these two terms. Then you have 1/3 into z raised to -1 plus z raised to -5. So these two terms are done. And you have z raised to -2 plus z raised to -3. So these two terms are taken care. And you have a single term that is 1/4 z raised to -3. Okay. So z raised to -0 and z raised to -6 has to be added together. So I'm drawing a summer over here, and the values, let me copy this one first. Okay. So you can take the summation. You can take the summation, one from this point, another one from this point. This is my x of n, and this has to be multiplied with one value. So what should it be multiplied with? Anyone? Anaka?
1/2.
This should be multiplied with 1/2, and the next term we have, one second. Okay. So you have a summer over here, and that need to be added with these two values, and that has to be multiplied with 1/3. So I'm tapping from this point and I'm multiplying it with 1/3. So that is done. Then you have the next one. So I'm taking another summer and I'm adding these two together. Okay. And I'm tapping from this point, and that needs to be multiplied with 1. So I'm not putting any gain. And at the end, you have 1/4 z raised to minus 3. So z raised to minus 3 would be available at this point. So you can tap it from here, and that needs to be multiplied with 1/4. And then all these things has to be added together. So I need to get a summer over here and another summer over here and another one here. Okay, then you add all the values. So this has to be added with this one and that with this one, and the output would be available over here. That is my y of n. Okay, so this is the linear phase realization of the given transfer function. Okay, so before I move on, let me just discuss another example. Okay, so this is actually for a cascade realization. Okay, so the question is, obtain the cascade realization with minimum number of multipliers for the system function. Okay, so we have to have a cascade realization. At the same time, it has to be done using minimum number of multiplications. So minimum number of multiplication is possible only if the polynomial is a system function representing a linear phase system. Okay, or linear phase filter. So you have two different polynomials over here. So do you think these individual polynomials can be realized using linear phase realization? Can anyone reply me? Devika, what do you think?
Yes, sir.
Can these two, do you think these two polynomials can be realized in a linear phase form or linear phase realization?
No. I mean,
Okay, so all right, you look at the first polynomial. So is this you just take the first polynomial alone. So can this polynomial be realized using a linear phase realization? Devika again.
yes.
Okay, what about the second one? The second one alone?
Yes.
Okay, these two in polynomials individually can be realized using linear phase realization. Okay, so the first polynomial needs 2 delay elements. The second polynomial also needs 2 delay elements. So you can realize them individually, then you cascade them. Okay, so let me quickly draw it also. So here you have the first delay element z raised to minus 1, and you have the second delay element z raised to minus 1, and you have the input over here x of n. Okay, and you can connect these delay elements together. Then you have to have the summer on one summer has to be put at this point. Okay, so by doing so, you are actually grouping this term and this term. One is without any delay, the second one is 2 delays. So you can take to this point and you take it to this point. So you have taken care of these two terms, then you multiply that with 1/2. Okay, and second term, the middle, you have z raised to minus 1. So z raised to minus 1 is available at this point. You can take that value over here. So you got z raised to minus 1 also 1/2 into z raised to minus 0 plus z raised to minus 2. And these two can be added together. These two can be added together. Then that is taken over here. And here you will get the output of the first structure. Okay. Now what you can do is you just take the entire structure, then you take it to the right. Okay, and you do not need this x of n over here. Okay, and for the second polynomial you have different coefficients. So the first coefficient is 1 and 1, so this should be multiplied with 1, and z raised to minus 1 is multiplied with 1/3, so this would be 1/3. So you have realized the first structure individually using linear phase realization, the second one also using linear phase realization, and the only step remaining is you have to cascade it. Okay, so the output of this one is connected to the input of this one, because if you have two different factors multiplied together, that has to be cascaded back to back. Okay, so this is in fact the cascade realization, as well as each of the cascade forms are, or individual forms are realized in linear phase realization. Okay, so I'm keeping this screen just like this, and if you want to note it down, you can note it down. Okay, otherwise it will be available in the notebook. Okay, so you can leave now. I will give you time in the next class to so there are several absentees today. What happened? Only 31 students are in the class.
Sir, exam
Any
is the
reason?
PGT.
Okay. So let me quickly take your attendance. 1 second. So 29 plus 2 is 31. Okay, so currently 29 students are there. Okay, let me save it. Okay, so you can leave now, and I think afternoon some few students have the Viva exam, so I will inform the time and the slot, so you just appear for the Viva accordingly. Okay, you can leave now. Bye.